Hey guys, in this video, I'm gonna give you some background information on Way ANOVA. So this ANOVA, the full name for ANOVA is analysis of the variance. So this is basically analysis of variance. So basically, it all comes from the variance formula, right? Sample variance formula. You can recall that from MA 222 statistical analysis course. Sample variance. So we're using the symbol s squared, which is equal to summation of x and n times summation of x squared, right, minus summation of x squared, that dividing by sample size times sample size minus 1. And then what they're doing is they just basically dividing every single term here by sample size n. Okay, divide by n here, divide by n here, divide by n here. And we'll be able to get down to the formula. So summation of x squared, so this n get cancelled. Summation of x squared minus summation of x square that divided by sample size, that becomes the numerator, and denominator here n get cancelled, we get n minus 1. So this is basically the foundation for the Way ANOVA, right? And then we're going to go into the detailed calculation step by step, how we apply this formula to understand the variance. Okay, so basically the example here is one biomedical field. So independent random samples from two population of serum uric acid values, right? So sample one, we have 10 numbers here, right? So sample size is 10. Okay. Sample size is 10. So sample two, same thing. Sample size is 10. And for sample one, if you're adding all those numbers, you get 10.6. So the mean is 10.6 by 10, and with 1.06. Second sample, the total for those numbers is 16.1 divided by 10, you get 1.6, right? So this is the first impression on those two samples. Now, so basically, what they do here is, first of all, they combine those two samples into a big sample. They call this total, sum of the square total worksheet, right? Look at this. This is sum of the square total, which is a very important element. And I'm going to show you how they arrive all those numbers here, step by step. So I'm going to just okay. First of all, keep. Okay. So all of these are embedded Excel files, so you can just click on it, and then you can just go to that and then highlight the entire data set, right? I'm going to run through the calculation here step by step, and then you can copy paste into the Excel. So you can just copy, paste this file into Excel. And once you do that, you're going to get something like this. Okay. So I'm going to walk through this calculation step by step. So this is like the combined sample. So the sum of the square total calculation here, right? SS total. Calculation. And let's go through this step by step. So first of all, by applying that formulas, so we need to sum, right? We need to sum up x, right? We need to sum up x squared. And then first thing we need to get x squared. So we're just gonna square all the x values. So basically in this case it will be C2 squared. Okay. So get out of that. And then once you have one calculation, then you can drag this. So put a cursor, you see the green box here, put a cursor on the bottom right hand corner. And if you drag it, you go all the way to the bottom and get all the x squared, right? And now we're just gonna sum up the x values, so you can do a quick auto sum right here. Go to home, click on sum, you get total here 26.7. That's total of x, and total of x squared. And quickly do an auto sum, get 39.65, right? So the sum of the square total come from these steps, right? So we get the total first, that's sum. So the mean, so we do the total, 26.7, divided by 20, because we combine both samples. So sample size right now is 20. So get 1.335. Then you're also going to do sum of the square divided by sample size. So it's 26.7 square divided by sample size 20, right? That's how we get that number, 35.64. And then sum of the square total will be difference between 39, sum of total of x squared minus total of x parentheses squared divided by sample size. So it's 39.65 minus 35.64. So I get 4.01. And that's basically the numerator, right? And then we're going to divide that by the denominator. So if we go back really quickly, we are looking at this formula we talked about earlier, right? This formula right here. So this is the numerator. Numerator is the sum of the square. And dividing by that, sample size minus 1 becomes the sample variance. And that's why we have this here. So dividing sum of the square total by sample size, which is 20 minus 1. That is, right? So 0.21. And after that, we're taking the square root of the variance. We get the standard deviation, 0.21. We get this. Okay. So sum of the square total, that's basically what we need, right? So this how we do the calculation here in the spreadsheet. Let's go back to our PowerPoint. Now, so up to this point, so we get all these numbers. Okay, that's what you see from our PowerPoint. The next thing we're going to move on to the individual calculations. So similarly, if you click on it, you're going to see an embedded spreadsheet, right? Excel spreadsheet. So you can just copy the entire both samples. You can do, right? You can just right click on it and then copy and then paste, right? And then paste into the Excel, and we can run through the calculation one more time. You're going to see something like this: sample 1 and sample 2. And now from here, first of all, we'll just zoom in a little bit so you can see better. So let's square the first sample number 1, square each individual data values. So you're going to do equal to this B3 square. Get out of this. Drag it, you get all the square terms. Same thing for the second sample, square D3, okay, and drag it all the way to the bottom. Now we're just add up this x values. That's the total of x, sum of the x, right? And add up x squares. That's for the first sample. Second sample, similarly, add up x, right? Total of x, add up x squared. Then we get all these numbers. So let me just quickly format this. Okay. All right, so now we're going to calculate the mean first, right? So we do 10.6 by 10, right? To get the mean, 1.06. And next thing, sum the square by sample size. So this is sum of the x, total of x square by sample size. So 10.6 square that by sample size 10. Okay, so get this. And the sum of the square total, it's going to be 12.06 minus, right, sum of the x square here minus sum of the square by sample size 11.236. So get this, and then variance, after that we divide by sample size minus 1, so 0.824 by sample size, which is 10 minus 1, get this number, And after that, we take in the square root. So I'm just going to run out of this result to 2 decimal place in a second. So square root of the previous number, right, be 17, get this. Let me just run it to 2 decimal place. For my cells, and we're just going to scroll down a little bit. Let's go to numbers, 2 decimal, that's good. So you're going to see a consistent result like what we see from the PowerPoint. And same thing for the second sample, we do the similar thing, right? Mean is a 16.1 by 10, okay, look at that. Sum of the square will be 16.1, square that, dividing by sample size n. So get this, and sum of the square total. So we find the difference, 27.59 minus 25.92. Get that, and then variance is going to be 1.67 divided by sample size 10 minus 1. And then also we take in the square root to get the standard deviation. Yep, so that's what you see from the PowerPoint. If we go back a little bit, right? So that's everything we see from the PowerPoint here. I guess they use 3 decimal, so I'm going to go back and change to 3 decimal. Okay. 3 decimal. For my cells. Yep, it should be exactly the same as what you see from the PowerPoint. Okay. So basically that's so the sum of the square within, that's the most important thing we're talking about here, right? So and then it's part of the ANOVA result. We're going to see in a second. All right, so now the next one you're going to see this. So sum of the square within. So adding those two numbers from the Excel, right? So adding these two numbers end up with sum of the square within 2.493, and then sum of the square amount will be sum of the square number 1, and then sum of the square from the sample 1 divided by sample size 10, adding sum of the square from sample 2 by sample size n, which is 10, and then total square by sample size. We did all those calculations, it come out with 1.51. Right? So the sum of the square amount is 1.51. And we're going to run through this hypothesis testing. As I mentioned earlier, it's an ANOVA test. It's a hypothesis testing test. ANOVA. It's basically a typical hypothesis testing. Hypothesis test. So HO is, we want to make sure two populations have the same mean, right? Population 1 and population 2. H1, some textbook using H1 is mu1 not equal to mu2, meaning two populations has different means. Okay. The assumption here is we have independent random samples or normally distributed, and then variance for population 1 the same thing as variance for population 2. And alpha is 0.05. To test this, we're using ANOVA, which is F-test, doing the F-test. Okay. And the rejection region is reject HO, meaning mu1 equal mu2 if F value mean of square amount. So mean of square amount is the sum of the square amount divided by degree of freedom amount. So degree of freedom amount is number of the samples minus 1, or the column minus 1. So in that example is 2 columns, 2 samples, 2 minus 1, which will be 1. Degree of freedom within, we have a total combined sample size of 20 minus number of columns, right? So it will be 20 minus 2, which is 18. And alpha, so alpha equal 0.05. Okay, degree of freedom amount, that's 1. degree of freedom within, that's 18. And based on those three values, we can go to the F table. So go to our Blackboard course and then click on the syllabus, textbook, and tables. Right here, you're going to see statistical tables. And you're going to open the F table. Okay. We can open the file itself. So we need three things to get a critical F values. The first one is the degree of freedom 1 on those columns, right? So degree of freedom df amount is 1. Degree of freedom within df2, that's 18. Okay. And alpha equal 0.05. So for the entire table, alpha is 0.05, right? That means area on the right tail is 0.05. And they're going to have intercept 1 and 18. The intercept is 4.41 right here. Okay. 4.41. And that's the critical F values. That's how you find the critical F values. Okay. So that's why you see this 4.41 here. Okay. But that's a and then test statistics F value is a mean of square amount over mean of square within. Mean of square amount is the sum of the square amount by degree of freedom amount. Mean of square within is the sum of square within by degree of freedom within. And it's summarized in this table right here. So degree of freedom for amount is 1, degree of freedom within is 18, right? So the sum of the square amount is 1.51. And 1.51 divided by 1, we get 1.51. That's mean of square amount. So in this case, mean of square amount it's 1.51. And then degree of freedom for within is 18. Sum of the square within 2.49. So mean of square within it's going to be sum of the square within which is 2.49 by degree of freedom 18, and that's approximately 0.14. Okay. So that's how you see 0.14 right here. And then F value is a mean of square amount by mean of square within. So this value comes from 1.51 divided by 0.14. Okay. That's approximately 10.78. And the conclusion here, right? So this is ANOVA result. Okay, we can easily get this result. I can show you in a second how we get this result. Yes. And then, so the conclusion here is since F value mean of square amount over mean of square within, it's 10.78, which is much bigger than critical F values. This is critical F value, 4.41. We get it from the table in the Blackboard. So yeah, so once that's happening, meaning the p-value is very small, right? Same thing as saying p-value less than alpha, less than 0.05. Then reject HO. So that's our conclusion, meaning the two populations have different means. Okay. Now very quickly, I'm going to show you how to get this ANOVA result from this Excel, right? So let's go back to Excel. Okay, then we're gonna just copy the entire table here. Copy, we'll paste into the similar. So here I'm gonna delete this. Okay, I'm gonna delete the entire column here. So I'm gonna delete this and here too. Delete. Okay. So basically, we just run the ANOVA using these two samples here, sample 1, sample 2. I'm going to quickly format this for our borders. Now, first of all, you're going to go to Files. Underneath File, you go to Options, and under the Add-ins, click on Add-ins. Now, Excel add-in Go, right? And you're going to check this particular option here called Analysis Tool Pack, right? Check it. Click on OK. Now, from there, when you go to data, you're going to see data analysis. Okay, and you click on it. So basically, most of the test and the statistical test will be available here. We're doing ANOVA single factor, right? So this is single factor. It's only one factor. Okay, click on OK, and then just highlight the entire table here. Labels in first row, yes it is. Output range, you're gonna pick alpha equal 0.05. That's good. Go by columns. I'm gonna put it underneath it. Okay, so under B14. Click on OK. So you're gonna see all this ANOVA results, right? See, I will be. So I have a couple things among groups. We have two different groups. Okay, and within groups. Okay, and then sum of the square, degree of freedom. If you run it to two decimal place, it will be very similar to the one we have here. I'm just gonna run this to two decimal place. Degree of freedom. Now this degree of freedom, we don't need the decimals. Yes. Okay. As you can see, we get this all this result, and then critical F value is 4.41, two decimal place. That's exactly what we have on the PowerPoint. And we basically just analyze this result and then get a conclusion from here, right? Okay. So as you can see, right, whatever we did earlier, it's all summarized in this ANOVA output. And for you guys, first of all, you should be able to understand the detailed calculation to show you step by step. Also, ANOVA output, that's also very important. If you look at this, F value is much bigger than the critical values. This indicates reject control, right? Meaning reject control indicates mu1 is not equal to mu2. Mu1 not equal to mu2. Meaning those two populations has different population mean. Okay. Symbols not equal to mu2. So that's basically what we have here. So getting ANOVA output is quite straightforward, right? So it also helps us understand the conclusion here, step by step. Okay. So now I'll just explain all these detailed calculations and then also the ANOVA outputs. So typically in a okay, so this is 3 samples. All right, so this is example number 2. So we have independent random samples from 3 populations of serum uric acid values. Okay, so similarly, sample 1, sample 2, sample 3, we add another sample over there. And similarly, you can run through this ANOVA worksheet, right, step by step. Try this on your own, see if you know how to do this. Again, one more time, you can just click on it. It will show you the detailed calculation step by step. Look into that if you have any question, how to get all those numbers, right? Just follow the earlier examples. You'll be able to understand each one of these numbers here. Okay, and we get this result here, and again, based on the result, we perform a hypothesis testing. Okay. So first of all, sum of the square amounts we get from the previous slide, right? Sum of the square amount, right? Which is this adding 0.824, 1.669, 1.169. And so yeah, sum of the square within, which is 3.662. Sum of the square amount. We go back a little bit. Okay, so you're gonna get 5. So you're adding those 3 numbers and subtract by the total here. Yes. You're adding 11.236, right? Adding 25.921, 22.205 minus 57.685. Okay, again 1.673. So the sum of the square total would be adding those two groups, right? So we get 5.335. So that's it. And we perform the hypothesis testing. So population HO is population mean for sample for first one, equal population mean for second one, population mean for third one, and alternate hypothesis is those three population mean are not the same. Okay, the assumption is same. Independent random samples is normally distributed, so all the variance, population variance are the same. Alpha equal 0.05 using ANOVA or F-test, right? Same thing. We're talking about ANOVA is F-test. Yeah, doing here. F-test. Okay. And for so reject HO if F equal mean of square amount over mean of square within is greater than critical F values. And in this case, we have a C equal to 3 samples. So degree of freedom amount is 3 minus 1, which is 2. Okay, that's C2 here. Degree of freedom within. So we have a 30 sample size 30 minus 3 different samples and 3, so it's 27. That's how you see 27 here. So same thing, alpha is 0.05. It will stay the same. And yeah, so based on those 3 values, we can find the critical F values. Okay, let me just quickly show you in our F table, right? So degree of freedom df1 is 2, df2 degree of freedom within it's 27. We have intercept is 3.35 here. Okay. That's why you see 3.35 on the PowerPoint. Okay. And then F value, test statistical F value is going to be sum of the square amount, which is 1.67 divided by degree of freedom. So 1.67 by 2, it turned out to be 0.84, right? So mean of square amount equal to sum of the square amount over degree of freedom amount. So that turned out to be 1.67 by 2. That's approximately 0.84. It's 0.835, but if you run it through decimal place, that'll be 0.84. And then mean of square mean equals the sum of the square within divided by degree of freedom within. So the sum of the square within over degree of freedom within. So degree of freedom within is 27. So now to be 3.66 by 27. That's approximately 0.14. And then you do mean of square amount. So F value equal to mean of square amount over mean of square within. That's turned out to be 0.84 by 0.14. That's approximately 6.00. If you look at this is test statistics. It's much bigger than the critical F values. This is critical F values. So that means we reject HO. So reject HO. We can also quickly confirm this in ANOVA output. So you can just copy those 3 different samples. Okay. Click on it. So we're just gonna copy all those 3 different samples. Okay, copy that. Now go to Excel. Open a new sheet on the bottom. Paste it here. I'm gonna delete all those space here. Put all those 3 samples together. Delete it. Okay, so now we get this. All borders, bolded. Okay. Now again, go to data and data analysis. So we're doing a one-way ANOVA, right? Single factor, same thing as saying one-way ANOVA. So we're gonna just highlight all those data values. Okay, this one. Yeah, if you just highlight all those data values without a title, that's okay, right? But I'm gonna highlight the title as well. So we have sample 1, sample 2, sample 3, labels in first row, titles in first row. That's good. Alpha is 0.05, upper range. I'm gonna put the upper range here, B14. That's good. Now you're gonna get all those outputs here, right? Excel outputs, ANOVA outputs. As you can see, our numbers will look very similar to the one we have in our PowerPoint. So if we run this to 2 decimal place, you're going to see the same numbers. Okay, just print that 2. 0.84 by 0.14, that's approximately 6.00, right? But Excel is using the exact numbers, so that's why it's more accurate, but no conflict. Yep, so sum of the square between groups among groups, right? Among those 3 groups. Degree of freedom is 2. Okay, we're just gonna highlight this, format a little bit, center that to get this output. F value is 6.00, but it should be, if you're using the exact numbers, if you run it, it will be 6.00, but Excel usually use the exact numbers, so that's why it's slightly more accurate. But as you can see, the p-value is very, very small, right? So p-value is, you can also look at the test statistic F value is much bigger than critical F values. This is critical F values. So that means we reject HO. That tells us that population mean 1 is not equal to population mean 2. Right, so those 3 populations have different means. That's what this is. Okay, and that's our conclusion here. So we end up with the hypothesis testing. Yes, so that's basically, you look at the ANOVA outputs. If you do it by hand, step by step, you get the same thing, but it's so much more convenient using the Excel. Yeah, and you are responsible to use the Excel to complete some Excel project later. I will show you from there, but yeah, that's how they get all these numbers. Okay. So you need to understand how to do it step by step in Excel, or you just also understanding the Excel outputs and interpret those. So example 3 is also a very similar one. So we have 3 different groups. Sample size equal to 10 was taken from each of 3 populations of young males. Systolic blood pressure measurements were taken on each child. Okay, so then the measurement are listed below, right? So we get this 3 different groups. We try to compare them, make sure, understand whether they have the same average systolic blood pressure among 3 different populations here. And this is another worksheet. Similarly, you can just go back here. You can click on it, and you'll be able to see the Excel spreadsheet here. This embedded spreadsheet, and you can just copy paste it into the Excel, and I run analysis from there. It'll be the same as the previous two, right? Very similar one. And again, we try to understand what happened, sum the square amount. Go back to the previous one, sum the square amount, it's add up all those three, sum the square, and minus the total. Okay, so here, those three numbers, 111,936, adding 94,478, and 93,123 minus 299,001. So that's the sum the square amount, three different groups. And then sum the square within, we do 708 adding 202 adding 1135. Okay. Yes, so add up those numbers, you get this total here. Sum the square total, you just add up those two numbers, you get sum the square total. And we perform the hypothesis testing, we make sure three populations is the same population mean. And similar assumptions here, independent random samples, they are all normally distributed with the same variance. Alpha is 0.05, and then test statistics ANOVA. We're still doing that test. Okay. And similar criteria, rejection region, we're using the critical value method, right? So reject HO, meaning mu1 equal mu2 equal mu3 if F value, test statistic F values is bigger than the critical F values. In this case, alpha is 2.05, C is 3, so the degree of freedom amount, those three different groups will be 3 minus 1, 2. And the sample size is 30, so degree of freedom within 30, total combined sample is 30, minus number of groups 3, so it's 27. And based on those three, we get this critical F value is 3.35, just like the previous one. And then mean of square amount is the sum of the square amount divided by degree of freedom amount. Mean of square within, sum of the square within divided by degree of freedom within. So in this case, sum of the square amount is 536.47 and divided by degree of freedom amount, which is 2. Okay. That's how we get this mean of square within 268.23. Again, all of those numbers in PowerPoint has been run into 2 decimal place. In Excel, they will keep the exact values, so the Excel will give you more accurate results, right? And the mean of square within, similarly, sum of the square within is 2043.70 divided by degree of freedom within, which is 27. That's approximately 75.69, which is this number. We divide those two numbers, get a value. Okay. And turn out to be a value is 3.54. So this comes from MS amount over MS within. So 260.23 by 75.69, we get these F values. And we reject HO because the test statistics F values is slightly bigger than the critical F values. So that means mu1 is not equal to mu2, not equal to mu3. So similarly, if you want to run the analysis in the Excel, right, you can just quickly do that. Okay, then click on it. This the entire samples. So you just highlight the entire table. Right, click on it. You see copy, and go back to the Excel. And the sheet 5, paste it here. Okay, so there are 3 groups. Okay, just format that a little bit. And we're gonna get the Excel outputs in a second, ANOVA outputs. So again, you highlight the entire table here. Okay, go to data, data analysis, ANOVA, one-way ANOVA, single factors, one-way ANOVA. Click on OK. And we're going to talk about two-way ANOVA in another video, right, in a second. So here, B2 to B. So highlight that. Labels in first row, that's right. Output range will be B14, that's okay. So you see the output here. Okay. As you can see, it's going to be almost the same as what we see from the PowerPoint. But I'm just going to, first of all, let me just center this. Okay, bold it. Okay. I'm putting all borders. All right, so same thing right here. The p-value is smaller than 0.05, so meaning is highly unlikely, so reject HO. Also, the test F value is slightly bigger than critical F values. This is critical F value, so reject HO. Right? That's the conclusion. Reject HO. And does that mean the population mean mu1 is not equal to mu2? Not equal to mu3, so the three population have different population average, right? Population mean, and that's what the result tells us. So that will actually give us the end result for this hypothesis testing, and that's pretty much everything in this video. Okay. So again, use the Excel wisely, right? Run through the calculation if you need to. So that's like sum of the square total calculations, sum of the square amount, right? Calculations, and give you guys some background information on one-way ANOVA.